So in this video we are going to review mechanics of materials for minor 1 exam. Okay, so for minor 1 the syllabus is one is about axial element, okay, and another one is torsional element, and the third one is bending element. Okay, so let me put a small picture. So in the axial element we will be applying the load axially. Okay, in the torsional element what we will do, we will be considering as an axial, not an axial element, a shaft kind of thing with the circular cross section. Okay, it can either be solid or hollow. Okay, and here we will be applying torque. Okay, so that's how the torsional element will experience the external load, and in bending moment and the bending element will experience a bending moment like this. Okay, fine. So now in axial element, first what do we calculate is the reaction forces. Okay, so similarly in torsional element we will be calculating reaction torque. Okay, and in bending element we will be calculating the reaction bending moment. Okay, fine. So that will be our first step. Okay, and the second step is in the axial element, the second step is calculating the internal forces. Okay, so the internal forces we denote that as N. Okay, and this is our x-axis and it's going to be a function of x. Okay, similarly here in torsional element we will calculate internal torque. Okay, and we are going to denote that as T, and here what we are going to do is we are going to consider this as Z. Okay, so T is going to be a function of Z. Okay, and what about bending moment? In bending moment, once again this is going to be X, so our bending moment which we are going to denote as M, which is also going to be a function of X. Okay, now the third step is, as a result of the internal forces, there's going to be a distribution. Okay, and we are going to use a measure called stress. Okay, so here we will be using axial stress or normal stress. Okay, so normal stress, which we are going to denote that as sigma of x. Okay, which is nothing but n of x by a, that could also be a function of x. Okay, in the torsional element what we will do, in the place of sigma we will be calculating tau. Okay, we will be calculating tau, which could be a function of z, and what is the formula to calculate tau? From T, which is equal to T by J into rho. Okay, so T can be a function of Z and also J can be a function of Z. So that's the formula to calculate shear stress. So this is actually shear stress. Okay, and here once again this is normal stress. Okay, normal stress, but the relation between normal stress and the bending moment is as follows. So sigma, okay, which is equal to m by I into y. Okay, so what is this y? For example, this is our cross section area of the beam. Okay, and there will be some axis which is called neutral axis. Okay, so y represents the distance from the neutral axis. Okay, so y represents the distance from neutral axis, I represents the moment of inertia. Okay, second moment of area. Okay, so that's about calculating the stress, and once we know stress we can calculate strain. Okay, so for axial element it's going to be a normal strain. And what is the formula for normal strain if we know what is normal stress? So epsilon of x is equal to sigma of x divided by E of x. Okay, so that's normal strain. And in torsional element, gamma of Z, which is equal to tau of Z divided by G, shear modulus of Z. So where E is the Young's modulus and G is the shear modulus. Okay, and here once again we'll be using because we are dealing with normal stress, so here once again it's normal strain, and we will be using the same formula. Epsilon is equal to sigma by the Young's modulus. Okay, and what is the fifth step? In the fifth step, okay, so for axial element we will be describing the displacements. Okay, so here the displacement is u. Okay, and how do we calculate u? What is the relation between u and epsilon? Actually epsilon, which is equal to du by dx. Okay, so that's the relation between epsilon and u. So once we know epsilon, then using this relation we can calculate what is u. Okay, so u of some x, which is equal to u of 0 plus integral 0 to some x. Okay, and epsilon of x prime dx prime. So that's how we need to do the integration, and we need to solve for u at some particular x. Okay, fine. So, and here what we will do is we will calculate something called phi. Okay, the angle of twist. And how do we calculate this one? So here we calculate from gamma. So the relation between gamma and phi is such that gamma is equal to d phi by dz. Okay, so that's the formula. So once we calculate this gamma, then using this relation, okay, so phi of z is equal to phi of 0 plus maybe let me put here integral 0 to z gamma of z prime dz prime. Okay, so using this relation we can calculate what is the angle of twist at different z value. Okay, now in bending element we will calculate something called radius of curvature. Okay, so radius of curvature rho. Okay, so how can we calculate the radius of curvature? So the formula is, let me directly write the formula, E by rho, which is equal to m by I. Okay, we'll be using this formula to calculate the radius of curvature. So rho is nothing but EI by m. Okay, so that's the way of describing the deformation. Okay, fine. So this is a review of axial element, torsional element, which the axial element which is in chapter 1 and 2, torsional element which is in chapter 3, and bending element which is in chapter 4. Okay, so these are the three elements which we have discussed. In addition to that, we have discussed few other things. One is say in the axial element, okay, say I am applying the load like this. Okay, now if I section this element with the plane which is perpendicular to the x-axis, say this is my x-axis, okay, then we will have some normal stress and no shear stress. And at the same time, at the same point, if I section it with some angle, okay, then in this section there will be shear stress as well as normal stress. Okay, so just check how to calculate the normal stress and shear stress for any arbitrary plane. Okay, so that is something you need to learn. Okay, that you can learn from I guess chapter 2. Okay, so that is one thing you need to learn. And another thing is E is Young's modulus, okay, G which is shear modulus, and there is something else called nu, which is Poisson's ratio. Okay, so the Poisson's ratio represents what is the ratio between lateral strain and the longitudinal strain. So that's the Poisson's ratio, and these three material parameters are not independent, so they are related to each other. So if two are given, then we can calculate the third one. Okay, so learn what is the relation between for example if E and nu are given, okay, how to calculate G. Okay, it's going to be a function of E and nu. Okay, and what is this relation? You need to know these relations. Okay, so that's one thing. And finally we have learned stress strain curve. So this is epsilon and this is sigma, and if you see, it will go like this, and then it will be yielding condition, and then it will go like this. Okay, so some properties we can learn from this stress strain curve. So one is the yield limit. Okay, so the point at which there won't be any inelastic deformation, but there will also be some permanent deformation which happens to begin. Okay, and that particular stress value is called yield stress, and we can denote that by sigma y. Okay, and then there will be a point where it will experience the maximum stress. Okay, so that's called ultimate tensile stress, so sigma u. Okay, and this one, the stress at the fracture. Okay, so maybe we can call that a sigma f. Okay, and whether the material is brittle or ductile depends on what is the strain when sigma is equal to sigma f. Okay, if the strain is very large, then the material is ductile. If it's very small, then it's brittle. Okay, then one more property is toughness. Okay, so which represents what is the energy consumed, okay, to break the specimen. Okay, and energy consumed per volume. Okay, so which is nothing but integral sigma d epsilon, so nothing but the area under the curve. Okay, so from for example, this is say epsilon f, then 0 to epsilon f. Okay, so that's the toughness, and there is another thing called resilience. Okay, which is again sigma d epsilon, which is the area under the curve, but this is from 0 to the elastic limit. Okay, so that's called resilience. Right, so that's all you need to know for this minor one exam, I guess. Okay, so just go through all the notes and all the problems from the book. Okay, so that will be very helpful. Okay, I hope we have covered everything, and thank you.